Hi, my name is Victor, and today we're going to be going over the root test, which is the last test for series convergence. Like the ratio test, the root test will tell us whether a series is absolutely convergent or not, rather than just simple convergence. So let's begin by reviewing some properties of the root test. So the root test states that with a series A of n, we can find out if it's absolutely convergent, divergent, or divergent by taking the limit as n goes to infinity of the nth root of the series. And doing that allows us to understand that if we were to say L was the answer, that if L was less than 1, that the series is absolutely convergent. If L is greater than 1, the series is divergent. And if L is equal to 1, this test is inconclusive. And we'll go in later into a proof allowing us to understand why these properties are so. But this test is perfect for functions which have an nth power in them, or series rather, with an nth power in them. And also, it's important and helpful for us to understand that we have to keep the absolute values around and make sure we take the 1 over n of the series. So, as a proof of the previous statements, we can see that the nth root of a to the n is actually a variation of a geometric series. It is a similar structure. If you were to raise the power of r to the power of n, you'd cancel both sides, and you have a to the n equals r to the n, which carries similar properties of a geometric series. Because in a geometric series, let's say 1 over 5 to the power of n converges because 1 eventually reaches 1 over infinity. And for, let's say, an integer greater than 1, such as 6 to the power of n, we see that it diverges. And the interesting point of L equals 1 is inconclusive because we have three variations, 1 over n squared, 1 over n, and negative 1 to the power n, 1 over n, which prove that it can be all three scenarios, convergent, divergent, or conditionally convergent. So now let's move on to some practice problems. So beginning with our first example, we have an infinite series, n equals 1 goes sigma n into infinity, of n to the power of n over 3 to the power of 1 plus 2n. So things to highlight here is that the numerator will mitigate out the n, power of n, which is perfect for the root test, and the denominator also has a 2n, which will get taken away with the root test. So let's begin by evaluating the root test on this function. We can see that first, if we apply it, we get the limit of n goes to infinity of n to the power of n over 3 to the power of 1 plus 2n. Absolute value, important not to forget that, the power of 1 over n. And this simplifies out to simply n over 3 to the 1 over n plus 2, which then eventually, because we can take out the absolute values because we know that this function is positive. And then continuing, we evaluate. We plug in, or we evaluate as it goes to infinity. We plug in infinity, we find that it's infinity over 3 squared, which is simply infinity. And because L equals infinity, which is greater than 1, we can decide, by analyzing our results, that this function would be divergent. So it's important to understand that the steps we did was first, evaluate the limit. Second, check if the limit was less than or greater than 1. And lastly, determine if it was divergent or convergent. And that's basically the trend you're going to have when you're solving with the root test. It's rather simple. So for our second example, we're going to evaluate another series. But this time, it's going to be from n equals 0 to infinity of 5n minus 3n to the cubed over 7n cubed plus 2, all quantity to the power of n. And this is the most obvious example to use the root test because it simplifies the function so that we don't have to worry about all these random powers to the n. We can just see. So following the same procedure as we did with the first problem, we're going to first take the entire quantity of the series, the power of 1 over n, and make sure to keep the absolute values. And doing so simplifies it immensely because we get rid of that 1 over n. We get rid of that power of n, and we basically make it as a simple limit function, which we've already evaluated numerous times on our pre-calculus days. And so knowing how to evaluate the limit as n goes to infinity of these kinds of series or now functions, we know that we have to first take or you look at the exponents of the numerator and denominator and determine if, are they greater than the numerator, because then it will diverge to infinity, or are they greater than the denominator, will it converge to 0? And lastly, we have to look at, is this function have the same exponents, and then therefore on the numerator and denominator, and therefore we can just take the fraction of the coefficients, in which this case it does. So therefore we can simplify this to simply -3/7, which is the coefficient of the numerator over the denominator. And then, not forgetting the absolute values, we realize that 3/7, which is L, is less than 1, and therefore this series does converge. For our final example, we're going to view yet another time where it's very easy to deduce that the root test is much easier, and I'll simplify the problem greater, because yet again we have -12 to the power of n in this function. And so we're going to evaluate. So yet again, evaluating this series, we see that by taking the absolute value of it to the power of 1 over n and evaluating the limit as n goes to infinity, we see that the limit of n going to infinity goes to -12 over n to the power of 1 over n, which simplifies to just n. And so because we have absolute values on the outside, we can just take them out and just simplify to 12. And since 12 is greater than 1, we know that this series diverges, because just going back to the structure of a geometric function, we know that it'll just be repeating and adding 12 over and over and over again and never reaching a convergent number, and therefore it diverges. And so in conclusion, the root test allows us to evaluate series which have some gnarly exponents with n's in them that just make the function a lot more complex, and it simplifies that so we can just get neater, cleaner functions, and simplifies it because we just have to take a limit of infinity, which allows us to see, is this going to diverge? Is it going to be infinity over x, or is it going to be x over infinity? Will it just be 0, or will it be a nice coefficient fraction, which is what we viewed in the second problem, and sort of evaluate out. And that's the goal, and it becomes very quick after you practice and practice. So I recommend you use a couple of these websites that I have shown here, because these websites have good problems, and I'll finish this video off with a solid worksheet which I think encompasses all 3 concepts we went over. And hopefully you have a nice day. Thank you very much. So just the common mistakes to remember to avoid are: 1, to take the nth root of the numerator and the denominator. 2, to remember that, for example, number 5, the n squared leaves a squared after you take the nth root. And lastly, to remember that n to the power of 1 over n is just 1. Good luck on this worksheet, and thank you for your time.